hit the record button. You are now being recorded, and I'm going to be asking Claire the first question. Well, I know I already asked you a question, but I'm going to ask you if you can see the unquiz in just a moment. Okay, so Claire, here is an unquiz. Can you see this one?
Yeah, I can see it.
Okay, excellent. I'm going to give you guys 10 minutes to work on this. And again, I know some student had their hand up with a question, and I mean, that's fine. We'll deal with questions later, but we're going to spend 10 minutes or so on this unquiz. And that may be enough time to do this. Jesse Hayes Carter would do this in like 2 minutes, but Jesse is better than many students. I mean, and I don't mean better as a person. I just mean he's quite a mathematician. But anyway, so I'm giving you 10 minutes to do this, and so please work on it. It is to your advantage to do this. Unquizzes are good. Okay, so please give this a go, and I'll talk to you in 10 minutes. Claire, my Fitbit says that it's been about 10 minutes. Can you still hear me?
Yes, I can still hear you.
Thank you so much. So everybody, Claire has graciously volunteered to be my deputy today, our deputy. She's helping us all. And so that is good, and I appreciate that. And Claire, I realize that I'm expanding the job a little bit, but can you also see the comments that are floating there?
I can see the chat, but I don't see any comments.
Okay, the chats, chat, that's what I meant to say. Okay, can I also ask you, as part of being my deputy, and again, I truly appreciate this, and I realize that, you might say, no, I have to refuse to do that. But are you willing to monitor that a little bit? And if there's something I should be aware of there, you'll kind of say, hey, you need to do, just let me know if you're willing to do that as well, please.
Yeah, I can do that.
Excellent, thank you so much. Okay, so Claire can hear me. That means everybody should be able to hear me. Now, these unquizzes actually are important. I know some students might say, oh, I will just play with my cell phone because, I'll benefit from this. You benefit much more if you try to do this. And again, I do these unquizzes because they have all the benefits of a quiz with none of the downside, because I'm giving you some credit for doing these. And you're grading them yourself, so there's no penalty there, and you do get to use your notes, although on a real high stakes assessment you won't be able to use your notes, and you grade them yourself, but it gives you a sense of, oh gee, I was able to do this problem, great. And maybe you didn't have time to finish the problem, but you get a sense of how long these problems take you and everything else. So I really like to do this. I truly consider this a part of the learning experience for you. And if you did attempt the unquiz, thank you for that. If you got the correct answer, congratulations. Otherwise, you've prepared your mind for learning and understanding the solution. So I'm going to go through this. Another thing that's good about unquizzes is that unquizzes I pick the unquizzes and I pick the test, the problems on your test. So I'm picking problems that are kind of like problems that you would have on high stakes assessment. And that's one of the reasons that I changed this, because you see, I'm going to expect you to sketch a picture of this yourself. And this stuff that's I covered up with the blue here, they're saying, oh, look at the picture. Well, yeah, but part of the whole thing is getting this. So anyway, I will read this and then we'll dive into the solution. And I will, pause. Your questions, of course, are always welcome. But I'm going to go through the solution, and I'm certainly going to pause either during the solution or at the end of the solution, or both, and poll for questions. So I want to do that. And then I know somebody had their hand up and they were wanting to ask some questions at the beginning of class, but I wanted to do this, but they will have an opportunity to ask the question later. Okay, so anyway, I'm diving right into this solution. Okay, first thing to do here is to draw the picture, okay? And so here's the picture. Now, this one up here is a downward opening parabola. And you know from Calc 1 how to figure out, where the vertex is. I mean, it's when the derivative is equal to 0. So this is minus 2x plus 6. You set that equal to 0. So that means the vertex of this guy, of this downward opening parabola, the red one, is at 3. So well, it's kind of like that. And similarly down here you have this one. And by the way, when you find now this is an upward opening parabola. And when you find the vertex of the upward opening parabola, you would take derivative, set it equals 0. So this is that's Calc 1. This is 2x minus 6. So this again, it is at 3. So you see the picture's kind of nice. Now you don't know what these points are yet, but we'll talk about that. But I got a downward opening parabola, I got an upward opening parabola, and so if you think about that, you say, oh, those are going to intersect, and we'll deal with these points, finding these points later. But that's what we've got. And then the problem also stated that we're revolving not around either x or y axis, we're revolving around the line y equal, it is x equal 8, which is this dotted line. So you see where you're revolving this thing around that. And again, the picture is a very important place to start. Now, I'm going to say a couple of other things about this picture just because I think I should. So now we have learned two ways to do this, and I didn't tell you a given way to do this, but we'll start thinking about slices. And so I'm just going to, and by the way, I guess I'm experienced enough. I do this pretty quickly, but I'm doing more slowly with you. Let's pretend you say, well, okay, I really like the disk washer method. So I'm going to see if I can, if that's a good one to do here. And so what I'm going to do is, if I'm using a disk washer method, I draw a slice, and I'm kind of wiggling my cursor, and normally people tell me, I'm not even going to ask Claire, but I think she can see that cursor. So I'm not asking you that. Okay, but anyway, so I'm drawing a slice that is perpendicular to the axis of revolution. I'm just really trying to see, oh, gee, is this a good candidate for me to use the disk or washer method? Well, when I do that, I get this, and I say, okay, so I certainly can draw that slice, and if I draw that slice, I would be integrating. If I'm drawing the slice this way, I would be integrating dy. But then I start thinking about it, and I say, well, wait a minute. If I'm doing that, it's going to be an inner radius and an outer radius, and so I'm having to do this dy. That means I'm solving this quadratic for x equaling a function of y. Now, you can do it, and Jesse Hayes Carver can do it, and I can do it, but it's not super easy for most students. It's kind of a pain in the ass, and it's really not that simple. And then you say, oh, damn, and I don't have to just do it there. I got to do it differently down here. And so you kind of say, ouch, I don't think that's a good way to do the problem, and that would be the correct solution. Now, but let's think about, well, okay, so what happens if I do the cylindrical shell method when I draw a slice perpendicular to the, or not perpendicular, it is parallel. This is parallel to the axis of revolution. Well, now I have the same, I didn't even talk about that, but you have to change functions that are on top of this. This is really a mess to do with the disk washer method, but with the cylindrical shell method, this is not so bad because the red curve is always on top and the blue curve is always on bottom. The slice looks like this, and if I draw the slice this way, I'm integrating dx. Now, I think I've mined everything out of this picture I can, but actually that's a lot that we have. Now, we still have to find out what these points are, and we'll deal with that on the next slide. But the picture, again, is a wonderful place to start, okay? So that was what I said about that. So now we're going to find these points of intersection. But you see, now I know that what I am studying is, I mean, I've made a personal decision that I'm going to use a method of cylindrical shells, and so that means I'm integrating dx. So that means I need to solve for these x coordinates, and so that's what I'm going to do next. Okay, so I set the two functions equal to each other, and here I get x squared minus 6x plus 9 equal minus x squared plus 6x minus 1. And the way you solve a quadratic is getting everything on one side, and so you move all of these things to the other side by adding or subtracting. This is like algebra, I suppose. And then you either use a quadratic formula, which, and actually I will tell you, when you're an engineer, you're gonna, everything doesn't factor. This problem happens to factor, which is good. You factor out the common factor. That's a good thing always to do. And then you can factor in this into x minus 1 and x minus 5 equal to 0. So that tells you that x is 1 and y is 5. Now you can get these y points if you want to have them. We actually don't need them for the problem, but you get these y coordinates by saying, well, if x is 1, you substitute up here, and if x is 1, you get 4. If you substitute into that equation, and if x is 5, and you substitute into, well, actually either equation, these are the points of intersection. Okay, so we have those points, so now we have all of that. So now we're prepared with the picture and all of that to start thinking more about the problem. Now, I realize this is a complicated picture, but we want to think about it. And in fact, maybe, I am going to talk about this picture, but I'm going back to this picture for a moment. Okay. Now remember, so what's happening is, pretend I drew a slice here, which is exactly what that next picture shows. So I'm drawing a vertical slice here, but I'm whipping that vertical, so pretend there's like a rectangle here, and I'm whipping that rectangle around this thing, and that my cursor flying about is supposed to indicate that. And I'm sorry we're not in the classroom, because in the classroom it would be way better, but that's what we're getting. Okay, so we're whipping it around that. Okay, and we know, well, we need to know the radius and the height. So the height is going to be pretty easy because of the way we drew our slice. The height is just going to be this function minus this function, because that's the height of this rectangle. But the radius is different. So here I am at 8. And by the way, this point of intersection starts here, so you have to think a little bit about this. But you're at 8, and if I took 8 all the way to 0, and I know I don't really go to 0, I'm only going to 1. But if I'm going here, what happens is the distance from here to that is x, and so what's happening here is that's not x anymore. The radius is going to be 8 minus x. I think maybe I talked enough to talk about this picture now. Okay, so you see from here to here it is x, but we're going around this one. This is the cylindrical shell thing we're drawing. So this radius is 8 minus x. Now the height is going to be the difference between the top function, which was this one, and the bottom function, which is this one. So if you take this guy minus this guy, you get a height of minus 2x squared plus 12 x, because a minus times a minus is a plus, and then you are minus 10. So this guy minus this guy is the height, and that gives you that. Okay, so now we're ready, really, because we know it. We know the formula is 2 pi RH, and we integrate that. Okay, so the radius is 8 minus x, and here we figured out that I called it the height, but it's the other dimension of it. I really would rather call it the height. They call the width here. Don't worry, but this is the other thing. So the area then is now they call it height. So the area is 2 pi. The area of the representative slice, and you do want to draw these slices, I think. Now, some students say, no, I am better than that. I don't have to draw the slices. I think they really help. But anyway, so the representative thing is 2 pi RH, radius times the height. So then, but that changes for every value of x. In fact, let me go back and say that again. You see that the height here will be some tiny one. The height here is the biggest it ever gets, but then it gets smaller again here. So you see, all of those things do depend on x. Okay, so we have, it is 2 pi RH, so it is 2 pi. I talked through why that was 8 minus x. This is the height. And now I got to do algebra, and there is some serious algebra here involved. 2 pi is just there, but you really got to multiply these things together and do that calculation. And so, I mean, there's algebra there, and certainly algebra is a prerequisite here. So you have to distribute or FOIL or do whatever you do to come up with this, but you should get 2 pi. And by the time you simplify this, you get negative 80 plus 106x minus 28x squared plus 2x cubed. Okay, and you got the 2 pi there. So now that's the thing we integrate. So down here, we're going to say that this is the volume is the integral from. Now, remember, we figured out that this was dx by drawing our slice. So we know that we're integrating from 1 to 5. We did that by solving some things there. There's the 2 pi. Just as tradecraft, I will tell you that as a practicing mathematician, I will jerk that 2 pi through the integral, not 10 times out of 10. You don't have to, but I do that. And then you're integrating all these things. Okay, so when you integrate minus 80, you get minus 80x. When you integrate this guy, the 106 just sits there, and this is x squared over 2. That gives you 53x squared. You come to this guy that minus 28 just sits there. This is going to be, I add 1 to the exponent divided by the new exponent. It is x cubed by 3, and that ends up being this thing. And then you come to this, the 2 just sits there, and we add 1 to the exponent divided by the new exponent. That is x to the 4th over 4. Okay, and that's what we have here, and then it's plugging in numbers. Now the pi, you don't throw away the pi. And if you had, and then for example, just the students sometimes ask, oh, well, what about partial credit? Well, the student did all kinds of work and told me that the answer was 640 over 3, because they forgot about the pi. They did a bunch of things right to get 640 over 3, but it's a sin to lose the pi because you gave the wrong answer. So that wouldn't be full credit, but that would, you're certainly getting 640 over 3, and oh, you lost the pi somewhere. That would be some partial credit. You would get substantial credit on this problem. Okay, so now what I'm going to do is I am going to pause, because this is what we did last time. Some students may have questions. I tried to do a credible job of explaining it. The questions that I'm asking for right now are about this problem that we just did. You will have an opportunity very soon, after we finish this problem, you will have an opportunity to ask, if a student wants to say, oh, is there extra credit in this class or something, you'll have an opportunity to ask that question. The answer to that one is no, by the way. But anyway, I'm asking questions here. So, and Claire, you can still hear me, yes?
Yes, I can hear you.
Excellent. Okay. So, and Claire, that's really important to me. And by the way, I was terrified yesterday in not in this class, but in a different class that I was teaching, because a guy agreed to do that, and then that certain student just vanished. And I did in my head, I thought, oh, F word, because when I asked, can you hear me, there was no response from the fellow, and I thought, my God, I lost the entire class. But then finally someone in the class said, well, I can hear you. And so I said, that's okay. And I'm not angry at that student, because I know crap happens and things like that. And some people say, oh, my baby's crying, or, whatever, crap happens. So I'm not angry at that student, but Claire, you're doing me a major service, and your classmates a major service with this. Okay, I'm going to start counting in my head to 10 Mississippi. I will always start the recount, but now we're open for questions about this problem. And my strong preference, although Claire agreed to monitor the chat, so if you're asking questions there, we can do with that. But my strong preference would be for you to go on mic if you can and ask your question there. So I'm just starting my count right now.
I have a question.
Please ask your question.
So in the beginning, when you're explaining, excuse me, when you're explaining which method to use, you said that with the washer method, the slices would be perpendicular to the axis of revolution, and then
that is true.
And then for the shell
disk or washer method, yes.
And then for the shell method, it has to be parallel to the axis of revolution.
Everything you said was true. In fact, if a student came into Learning Commons and said, I've missed class, I don't know about these washer and shell methods, where I would start is I would say, well, with the disk or washer method, you draw a slice perpendicular to the axis of revolution, and for the shell method, you draw a slice parallel to that. So everything you said, my student, is true. Okay, and those are actually very big facts to keep in mind. So and I don't know if your question was asking for clarification on that, but I agree with you 100%. That's exactly what it is.
Okay, I just wanted to make sure.
Okay, and good for you. Okay, and good for you in wanting to make sure, and good for you for actually saying it exactly correctly. Okay, now whenever I have a question and I think I've answered the question, I start my count again. So we're still open for questions on this thing.
Hi, Mr. Bradley. So I was wondering if this is going to be a question that's similar to what we would do on a test, would we at the end
Um,
we have to plug in like 5 into
yes.
such a large equation and then subtract it from 1? Because that might take a
Yes,
long time
yes,
and might be
possibly.
difficult.
Yes, possibly. Now, when I make a test, I really do think about the students and things like that. And I'm also going to tell the student who asked this question, everybody else, back in the day, before we had these VCMs and before we had to have things, I always put my test, and I mean, I had done this for several terms at the College of DuPage. I put my tests in the testing center. And so you see, when I did that, there would be no time limit on it. I mean, a student could come in and they would get to this and they don't have to say, oh my gosh, I don't have time to plug this in. No, no one is timing you. The test is not timed. In fact, and I'm sorry, but I'm digressing. I'm telling you a story. I worked in the industry for a very long time, and I was fortunate that I was promoted a few times, and I hired people to work for me who were way smarter than I am, and that was really great. And in fact, those people were so smart that they could do the day's work that I required of them. They could do that in 2 hours. They were that smart and that good. But I also had some people who were working for me who were not as quick as some of those other people. And they had to work 12 hours a day to do the day's work that I was asking them to do. Now, I loved all of the people who worked for me, but I got to tell you, I loved those 12-hour people a little bit more because they were doing what had to be done to get the job done. And I actually loved them a little more. Now, applying that here is, in a perfect world, and I'm really am getting to answer your question, I don't think tests should be timed. And that's the reason, in a perfect world, I put them in the testing center. And I just said, yeah, you know, in the testing window, go in there, find a time, and I don't care how fast you work, but you go in and you do the problem. So I would tell you that this would be a fine test problem for me back in the day when I was teaching Calc 2, before there was all this COVIDs and all of this stuff. This particular problem would not be as good to ask in this way, although I will tell you that I could ask pieces of this problem. For example, now, and by the way, I'm not saying I'm going to do this, but I could say, hey, set up the integral you would have to evaluate. And the answer there could stop right here where I'm wiggling the cursor. So I think this is a fine test problem. I think it's representative, but also given the fact that unfortunately in this era and in this delivery mode, the tests have to be timed. I would be cautious about giving you this problem where, and again, you can't use a calculator. So you know there's a lot of calculation here. But so back in the day, this would have been a great test problem. It is very representative of the kinds of problems that I would ask you. But I do try to write fair tests. And I also, what do I want to say? I also vet the test with Jesse Hayes Carver, and I say, oh, Jesse, here's a test. What do you think? Now, I take a little bit with a grain of salt. And by the way, I have enormous respect for Jesse. But Jesse would say, yeah, that's a good test. But Jesse would probably substitute these things in his head and do this calculation very quickly. And Jesse is not a typical Calc 2 student at all. So while I know I rambled a lot, but yes, the essence of this problem is this is a good test problem. That's why I picked it as an unquiz problem. And a student in this class should be able to do this problem. But there's a lot of calculation, so I would think I probably wouldn't ask this question exactly the way I did with these numbers and so on a time test. I hope I answered your question. I know that was a rambling answer, but I covered a lot of ground there, I think. Are you okay with my answer?
No, yeah, that works out. I just wasn't sure because it seemed like a lot of like without a calculator, it seemed like it might be like prone to making some like small mistakes.
This would take you a long time to do.
Yeah.
And by the way, I will tell you that probably on the high stakes assessment. There will be some problems that will take you a while to do.
Yeah.
Okay, but anyway, so I mean, I'm not trying to be unfair, but I just grabbed this. So anyway, I'm thinking that question is answered, and so I'm starting my count again.
Hi, I have a question. This is Dale.
Please go ahead.
And I apologize if this is what the first person asked because I had to step away for a second. But I just wanted to make sure. So if we draw the slice perpendicular to x, will we always be integrating dx?
Yes, yes.
Okay.
Yeah, in fact, I'm answering the question a little bit more. I'm going back to this this slide. You see, the slice is a very important thing. And so if you draw the slice this way, that means you're integrating dx. If you draw a slice this way, that means you're integrating dy. And so that's a huge thing. Okay, I'm thinking I maybe answered that question. I'm going to pretend that I did. And so let's see, what were we doing? Oh yeah, I don't know. Look, I'll just stay here for a moment. I'm starting my count again. Okay, I hit 10 Mississippi. Now, your questions are always welcome, but I'm moving on from this for now. Okay, so I don't know. Here's what I want to do. Okay, so we did an unquiz. That is good. Now, I'm going to start with a little bit of cockpit commentary, and then we'll go back and I'll open this for any general questions. But then this little 75, 10, 50, I'm just reminding you that, yeah, I do know what time it is, and we're going to work for 75 minutes or so because that's known to be the physical limit when anybody can listen to me continuously for that. So on or around 9:15, we'll take a break for 10 minutes. Then we'll come back and then we'll do the balance of the time that you paid for. So that is good. Cockpit commentary. This finishes our week. We will not meet tomorrow. So the weekends at the College of DuPage are Friday, Saturday, and Sunday. I want to tell you what I do on Friday, Saturday, and Sunday is I do math. And so I'm going to be doing math, and it allows me to catch up on some things. For example, there was one of your classmates, and by the way, I don't think it was anyone in this class, but there was a problem that I did, and they were having trouble with doing the calculation to get the number, and I sort of promised that student, well, I'll double check the answer and things. So I have things I need to catch up on, and maybe some of you students have things you need to catch up on too. You might say, boy, I haven't watched those videos, or I haven't done problems, or I haven't, there's all kinds of things. I haven't even looked at the LSA yet, or something like that. Well, this is a good time to catch up. Okay, so anyway, there is no class tomorrow. The next time we will meet as a class is on Monday after we finish today. So that's one thing of cockpit commentary. I think we're going to be in good shape by the end of this period. I think we're on course, on schedule. Now, there is some new material that I am planning on covering today. I'm going to deal with arc length and surface area of revolution. I'm confident that we can do a credible job on that, and that will be happening. But on course and on schedule, I think we're doing just fine. And so, but as from the cockpit, I also will say, keep your seat belts buckled because, things like that. And I hope some of you are attending Jesse Hayes Carver, or finding it able to attend Jesse Hayes Carver's guided study groups. And again, I have a lot of respect for Jesse Hayes Carver, and I'm proud to have him as a co-pilot here. So take advantage of him if you can, and there's all kinds of help that you can get. Okay, I think I'm going to be quiet now, and I'm going to go for I'm going to count to 10, and I want to field questions. And I suppose the questions could be kind of anything here because we didn't just do a problem. So I'm going to count to 10 Mississippi to see if there's questions. And there was some person somewhere along the line that raised their hand, and I wasn't blowing them off, but I also, and I don't know what the question was, but sometimes students say, is the book required in this class? It's not required. It's a good thing to have a calculus book, but there's ways to get by. You don't have to buy it. But but questions like that are even okay. So I'm counting to 10 Mississippi, but these are like broad general questions, I suppose. Okay, I hit 10 Mississippi, so maybe that student's question got answered, or maybe I don't know, but no one asked it. But please understand that your questions are always welcome. So I'm going to be diving into material here. I got to figure out these notes. Just bear with me, I'll be fine. And I am going to post some notes. That's one of the things I'll try to do over the weekend, is post some notes, but these are other notes. Okay. We're almost there. Here, okay, this is good. Now, I started talking about this in your class last time, and in your sister class, I didn't get to talk about it, but so I'm going to be real quickly covering that again here, and I realize that. But anyway, so arc lengths. So we're going to know how to find the arc length of a smooth curve that has a continuous first derivative. And then we didn't talk about this in your class, but finding the area of a surface of revolution. So this is mostly about arc length. So what we did in this class, I'm pretty sure, is we did end up talking about arc length a little bit. We started with the distance formula and went through a whole derivation of this. But this is where we landed in this class, I think. Is we did talk about the definition. So I'm sort of starting here with you guys today. Okay, so we have y equals f of x, and it is a smooth curve, and so that means it has a continuous first derivative. In this class, you don't have to worry about that too much, but that is a math requirement. So the arc length of f between a and b is, and s is notoriously used to represent arc length. So the arc length is, in fact, I think I'm going to modify this slide just a little bit over here. I'm going to put a comment in here. I'll say it differently. Often, we speak of ds, comma, where s is the arc length. And I'm going to say arc length parameter. Okay, and I'm going to make that red. I think that is maybe a good, crap. Okay, so how can I do this? Okay, so I think what I can do is there. So now I can make this red, and I've added it, and so now let's look at the slide. Okay, so S, the arc length, is equal to the integral from a to b, and this is the square root of 1 plus f prime, that's the derivative of f, whole squared dx. And that is if it is y equal f of x. But we've learned in this class that sometimes we're talking about x equal g of y. So then the arc length between c and d is s is the integral from c to d of the square root of 1 plus, this is g prime of x whole squared, all under the square root dy. Now often we speak of ds, where ds is the arc length parameter. So ds is going to be, it would be the derivative of this, so ds would be the square root of 1 plus f prime of x whole squared dx. And again, the problem that we're solving is this one. We're saying, oh, we want to know what's the length along the curve here. So s is the length following along the curve here. There was y equals f of x, and the other one would be, having x equal y of g. So that's what we're solving, and now we have a formula. Now, pictures are often good, And pictures, in fact, on those problems that we just were doing are, I think, essential. Here, maybe not quite as essential, but you'll remember the formula. So there is the formula. And I think I went through the derivation, and the derivation's in the slides. I'm pretty sure it's in your book too. So anyway, this is the formula that you need to know. And again, there's not going to be a formula sheet on the test. So whenever you start preparing for the test, you say, oh, I want to set up a little note card or something. And you can talk to Jesse Hayes Carver about this too. But this is a formula that you want to know. And again, one thing that I said was ds then is going to be the square root of 1 plus f prime at x whole squared dx, and that was under the square root. So ds is this guy that I'm wiggling my thing on my cursor under. Wow. This is a little bit of tradecraft looking ahead to be engineers, so I'm just going to read this. Definite integrals representing arc and length often are very difficult to evaluate. And that's especially true at this place in Calc 2. In fact, if I were writing a book, and that's never going to happen because I know how hard it is to write a book, and I guess I'm too lazy to write a book. But this really, studying arc length could happen later in a course where we have more integration techniques that we're going to study. Now, and I know I've told you this, but I'm working with a group of other Calc 2 instructors. They say, well, gee, we want to do things in a certain order, so this is the order in which we're doing them. So you see, and in fact, I do have an example later where we run across an integral that you don't know how to do. But I'm going to say you don't know how to do yet, because later on in this term, I'm going to teach you how to do that. But we're doing this one first because I'm trying to be a team player. I'm doing this in order. But anyway, so definite integrals representing arc length in the real world often are very difficult to evaluate. In this section, we'll do a few examples. And if you get more advanced integration techniques, you'll be able to do more and more of them. That means on the final exam, you actually could do more. And also, we're going to be talking about numerical integration in this course as a featured topic. And so you can do this, but setting up the integrals are one question, and then evaluating the others, and so we'll talk through that. Okay, so maybe that's all I want to say there. Let's look at an example. Now this is kind of not an exciting example, but I think it's a little bit of a useful example to go through. And in fact, the algebra in this will maybe be useful too. So we're just saying, what's the length of a line segment? So what's the arc length going from a point called x1, y1 to another point called x2, y2 on the graph of y equals, y is always f of x, y equal, well, no, it's not. Forget I said that. But here, y is equal to f of x is equal to mx plus b. Okay, so you see, you're saying, well, what's the arc length if I go along a line? Well, I'm going to just think about the problem broadly. You say, well, damn, that has to be the distance formula. So that is going to be, the arc length is going to be the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. That is the distance if we went along an arc. But what this example says is, well, let's test our formula and see if that's going to work here. And by the way, remember in our formula, we had an f prime. And so what's f prime here? Well, f prime here is just going to be m, which is the slope. But the slope here is going to be numerically y2 minus y1 over x2 minus x1. So this is just this is not an exciting example, but just saying, hey, let's test to see if this works here. And I decided to add this here. So this is what we're going to do. I would not ask you this problem on a test. Okay, now here I already said this, but f prime of x then is equal to y2 minus y1 over x2 minus x1. So now what we need to do is we integrate from x1 to x2 of the square root of, this is 1 plus y prime of x whole squared dx. Now that's the formula that you memorize and everything else. But now we know that f prime of x is this thing up here. So I substitute that in and I have this. And now I do some algebra underneath. And actually this problem maybe isn't as worthless as I was sort of making it out to be, because you do have to do on problems I will ask you, you do have to do algebra under the square root. So what we're doing in this next step, I've totally changed my mind on this problem. I think this is a worthwhile problem to do. We'll get a common denominator. So you see over here I have y2 minus y1 whole squared over x2 minus x1 whole squared. But to simplify this thing under the radical, I want to get a common denominator. Now the common denominator here, you see this is 1, but 1 is x2 minus x1 whole squared over x2 minus x1 whole squared. So I get a common denominator here. This is like, I don't know, algebra, pre-calculus maybe I will say. So we do that. So I have to multiply. This one is good to go, but this one I have to multiply top and bottom by x2 minus x1 whole squared. So I do that here. And so that is what I get. Now it is important for students to. Okay, so this is what I have once I do that. Now I have to integrate this. So this is being raised to the okay, and so this is dx. So I have to integrate this, and I have to plug in x2 and x1. So I integrate this. This is this business, but this actually, and it's important for you guys to realize, this is a damn constant, isn't it? Because you see x1, x1, y1, and x2, y2 are just constants. So all of this business here, really for fixed x1 and x2 is a constant. So really, I would jerk this constant out. This is just like 5. But then I would be integrating with respect to x. So it is like I pull the constant out here. I'm integrating from x1 to x2x. Well, okay, so that is going to be this constant. And this is just integrating dx, or x to the 0 dx. So you add 1 to the x1. So you get x, and I'm plugging in x1 minus x2 into the x part. So you get x2 minus x1 here. Now, what happens, though, is that you see here, I have the square root of x2. I think this actually is a good example now that I think about it. This is x2 minus x1 whole squared under the square root. That's in the denominator. So when you take the square root of that, and we're assuming that x2 is bigger than x1, and so you see this thing under the square root is going to whack with that thing, and all you're left with is the square root of x2 minus x1 whole squared plus the square root of plus y2 minus y1 squared, and all that's under the square root. Now this is satisfying because that means, oh, this did prove we got the distance formula, and the benefit of doing this problem is we got to practice a little bit of this arithmetic here. Okay, so I am going to pause now for a count of 10, and if you have questions, please leap in on this example. Claire, are you guys still out there?
Yes, I'm still here.
Great. Okay, and thank you so much, Claire. I truly appreciate what you're doing. Okay, and I hit 10, so I'm thinking, oh, there's no questions on that, so that is good. And here's a picture of what we were doing. Probably should have shown you the picture before. Maybe in your sister class I'll show you the picture. Now let's go to a more, I don't know if I want to say interesting or not, but another problem. And again, this, I mean, the examples I do also are like problems I could ask on tests and things like that. So anyway, I'm just reading the problem. Find the arc length of the graph of y equal x cubed over 6 plus 1 over 2x on the interval from 1/2 to 2. And it does say, as shown in the figure, you really ought to be able to graph this, but I don't know. Just when I'm putting this together, I didn't do that. I probably, I've got to tell you, I probably wouldn't, I don't know. Let me not speculate on that. I could just not give you the picture, but I gave you the picture here anyway. Now, you might be looking at this and saying, why in the heck am I interested in x cubed over 6 plus 1 over 2x? And you might say, well, that's what the problem says. The reason that people ask this question is that there's a little piece of math tradecraft that's buried in here, and I'm going to explain that to you, although it's not explained that way, because you might think, boy, what a goofy function. Well, they picked this function to kind of show you some tradecraft, and I'm going to underscore the tradecraft. Okay, so we need to do this. So this is y equals f of x, and so I'm supposed to find the arc length. So what I'm determining is I'm saying, well, and they told you you're going from 1/2, so x is 1/2 to 2. So they want to say, well, how long is it from there to there? So that's what we're doing. Let's just dive into doing the problem then. Okay, now first step. And by the way, there is a little bit of tradecraft here, so bear with me, and I might end up adding a note here. I don't know. We'll see. Well, okay, so we know that the arc length formula has dy dx in it, or in this case, it is f prime of x. So we have to take the derivative. So this goes back to Calc 1. And, you know, and so some students say, you mean I have to remember things from Calc 1? Well, yes, you do in Calc 2. And so anyway, we have to take the derivative of this. Now, this guy was, so we'll just talk about taking the derivative of this. They just write it down there. But if you take the derivative of this, the 1/6 just sits there and you're taking the derivative. Now, the derivative doesn't work like an integral, though. The derivative of x cubed is 3x squared. And the derivative, and here, I would treat this as 1/2 times x to the minus 1. Now, the 1/2 just sits there, but the derivative of x to the minus 1 is going to be minus 1 times x to the minus 2. So again, this may have been the first derivative we took in this class, but I just did it. So you have to know how to do that. So if you do the thing that I just said, you see here's the 3x squared, but you're dividing that by 6. And so that'll become 1/2 when you simplify it. And you do want to simplify things because if you have, I mean, it just helps with your number. So algebra is your friend, and so doing simplification is good. And here, this, I said this was minus 1/2 x to the minus 2, and that's what we get. But now simplifying this further, algebra is your friend, and the way this happens is you do a bunch of problems and you get familiar with it. And Jesse Hayes Carver would do this automatically, just on autopilot. But Jesse Hayes Carver has worked very hard to become the mathematician that he is. But anyway, the dy dx, but we're factoring that out. So what's left after you factor out the 1/2 is x squared minus 1 over x squared. Okay, now this is what we're going to square. And it's going to be right here because this is our formula for the arc length. So there's dy dx. We're going to have to square it. So we're taking this thing here, and I'm putting it in there, and I'm going to square it. And again, A and B were 1/2 and 2. And so this is just the formula. It's substituting the stuff in. And so this is the square root of 1 plus, and this is 1/2 times this business whole squared dx. Now, I am going to pause just for a moment to go back to what a student was asking me about. After I talk about tradecraft, this actually, I don't know if I've ever asked exactly this problem, but yeah, I would ask you this problem on a test. And you might say, oh my gosh, that's going to be an ugly integral. Well, not so much. And I'm not going to write a whole bunch of stuff, but I'm going to say, note there is some math tradecraft here. And I do want to emphasize that. I'll try to make this red, I suppose, for you and your sister class. Okay, so now I did that. I'll save that as a change and we'll go back. Okay, so I hope everybody is good to hear. And by the way, I'm going to pause for a count of 5 Mississippi right here. where I made the note of tradecraft. I probably should have put an arrow there, but anyway, do people have questions as to how we got here? So I'm counting to 5 right now. Please ask a question if you have it. Okay, no one asked any questions, so that's good. So now I will continue. Now what I'm going to do is I am going to square this, and I'm going to square this under the square root. So when I square this, this is 1/2 times this guy, but when I square it, I can say this is 1/2 squared times this business squared. So I'm squaring the 1/2, I get a 1/4, but that is 1/4 under a square root. So 1/4 under a square root, and this is a principal square root, this becomes 1/2 outside square root. So bear in mind, I'm going to do that later. So I'm squaring this, I'm making that 1/4. Okay. And then I'm going to go to this part. I'm going to say, what is x squared minus 1 over x squared? And wow, I'm going to go, and I don't know, maybe this is a mistake, but I don't think so. I'm going to go, and I need to go back to, where is it? Let's see. Okay, now I'm changing the sharing, Claire. Claire, can you see a whiteboard?
Yes.
Excellent, thank you so much. Okay, so what's going to happen here, and I know this will look like I'm a 2-year-old, but we'll do it anyway. So this was x squared minus 1 over x squared. Whole squared. Now, when I multiply this, I'm foiling it, okay? And so what I'm going to get is, and again, I don't have a lot of room here, so I'm just going to write it, but it's important that you realize that this is what's going on. This is the tradecraft I'm talking about, and this is why they did this goofy kind of thing. And those of you who are paying attention, to this lecture and things like that, or watching the lecture on a video and paying attention, or something will say, oh, gee, Jim could cook up something like this, and this could be, it could be a problem similar to this. So this is going to be x to the 4th. But notice when you get the middle term, that's going to be x squared times minus 1 over x squared. And so what's going to be happening there, when I take x squared times 1 over x squared, I get minus 1. And when I do that again, when I FOIL the other one, I'm going to get a minus 1. So your middle term doesn't have any x squareds in it. It's a 2. And this, of course, is going to be 1 over x to the 4th. Now, I'm going to do another one down here because this is anticipating what's happening. So this is my tradecraft comment. What is x squared plus 1 over x squared? I know it looks like I'm a 2-year-old here, but okay, well, it is going to be similar, except it's going to be this. It is going to be x to the 4th. Instead of having minus 2, you end up with a plus 2. Okay, so this is the tradecraft, and you know what I think I'm going to do? Let's see. I'm going to snip this, and I'm going to stick it in the, okay, so I need to snip this. Bear with me, I'm doing something here in real time. Okay, so I hit the snip button, that will be good, and I'm just going to copy this 2-year-old arithmetic here. I'm going to copy that, and I'm going to paste this into the slides, just like as tradecraft. So I will go here, a new slide, and I will paste it. Okay, I don't know if you can see what I'm doing or not. I mean, I don't care. I'm not hiding anything. This is just some tradecraft. Okay, and then I'm going to save that. And now I'm going to go back to Blackboard. And I'm going to pause for a count of 5 Mississippi. Do people understand what I did here with this a little bit of algebra?
So did you just show 2 different ways of foiling because of the plus or the minus that you have in between?
Right, but when I go, whoever is asking that question, thank you for asking the question. When I go back to the mainline thing, I'm going to say, oh, look, that's what happened here. And I got to tell you, I've taught this course many times, and some students say, WTF. So I kind of said, this is what's going on, okay? So just hold this thought, I guess.
Okay, because, sorry, that was going to be my question in step 3, I believe, because I can't see right now, but...
Well, we're going back to that, okay? And again, I'm not being rude, okay, when I say this, but right now I'm asking, does everybody understand what they see on the whiteboard? Okay, I got to 5 Mississippi, so I'm doing you do. Now, I am going back to the discussion, okay? But we might need this. Okay, so now I need to go, Claire, back to sharing my application screen. We'll see how that works. So I'm going back to PowerPoint, and I'm going here, and that's not what you want to see. I wanted to go back to PowerPoint. How come that didn't come? Oh, here it is. Okay, but now I'm going back to this one. Okay, so Claire, you should be looking at a slide that says solution at the top.
Yeah, you're all good.
Excellent, thank you so much. Okay, so now we're back. Now I said, note there's some math tradecraft here, so it's going to happen. Okay, so I squared the 1/2, but now I squared this puppy. X squared minus 1 over x squared whole squared. That's what I get. This is what I did. So this is x squared plus 2 plus 1 over this. You might say, well, wait, no, you showed us that this thing squared was minus, okay? But what I'm doing is this, it really isn't underneath here. It really is not, I'm adding 1 to it. So I'm adding 1 to 1/2. I'm adding 1 to minus 1/2. You see, there was a so this I'm adding 1 to 1/2, and so when I add 1 to minus 1/2, I get 1/2, which is 2 over 4. Okay, so you see I'm doing algebra here. So this is 1/4, okay, after you square it. So this is 1/4, and this is going to be, in fact, maybe I'm beating a dead horse. Okay, this is just doing the tradecraft that we get. So I added the 1 and I got to this. And maybe I was worrying more about that. Maybe everybody understood that, but that's how you get from here to here, was the tradecraft. But now, the second piece of the tradecraft, I said, oh, but the square root of 1/4 is 1/2. I jerk it through the integral. And the square root of x to the 4th plus 2 plus 1/4 is x squared plus 1 over x squared. So you see what looked totally nasty because of this tradecraft became totally benign. This is an easy integral to do now. So let's do the integral. Now the 1/2 just sits there, but if I integrate If I integrate x squared, it's x cubed over 3. That is good to go. Now this is x to the minus 2. So when I integrate x to the minus 2, I add 1 to the exponent, divide by the new exponent. The new exponent is minus 1, so that's minus 1 over x. So now I'm plugging in 2 and 1/2 into this, and that's just some pretty benign arithmetic. And you get these numbers. So the answer to this problem is 33 over 16. Now, and maybe you guys are, I mean, Jesse Hayes Carter would just look at this and say, yeah, of course. But at least when I've taught Calc 2 before, students have been concerned about this. But hopefully maybe my tradecraft avoided all that. So I'm pausing for a count of 10, Mississippi. I do know what time it is. We're nearing a break, but I want to deal with the questions on this before the break. And then maybe we'll even begin on another example. We'll see. I know what time it is. Okay, so I'm starting counting to 10, Mississippi, if students have questions on this problem. And Claire, you guys are still out there, right?
Yeah.
Okay, so maybe I did a good job explaining that. I hope so. Okay, let's go to another problem. Okay, so here is this problem, the next one. And again, I do know what time it is. We're going to take a break very soon. But we might be able to get started on this, and who knows, we might be able to finish this before the break. Find the arc length of the graph of y minus 1 whole cubed equal x squared on the interval 0 to 8 as shown. Now, by the way, one of the things that you guys are going to learn and in fact, let's go back and look at this just to remind you of this. We have two formulas. One is a dx formula and one is a dy formula. And you might say, well, when do I use which one? That depends on the problem, and that's something you're supposed to understand. Okay, so we're going to go back to the problem that was just at hand, and you say, oh, whoops, that's not the problem. This is the problem that we're doing. Oops, this is the problem we're doing. Okay, so you say, well, damn, I don't know. I'll have to think a little bit about that. And here I did sketch a graph of that one, because the point here is, doing the integrals, not so much sketching the graph, although sketching the graphs are important. Okay, so you see this is what's going on, and they tell you you're going from 0 to 8. So we're saying, oh, if we move along this curve, how far do we go? What is the distance from here to here? Find the arc length, okay? So we're just going to continue to go. We got a couple minutes, and we may be able to finish the problem. Okay, or maybe not. Okay, in fact, what I'm going to do is I'm going to talk about the problem, and then I'm going to entertain questions when we get back. Okay, now we're solving for y here, and so y is equal to x to the 2/3 plus 1. Then we have to take the derivative of this because there's a derivative in our arc length formula. So the derivative of this is, going to be 2/3 x to the 2/3 minus 1, which is 2 over 3 x to the 1/3. You see this is in the denominator now. So that is dy dx. But dy dx is undefined when x is equal to 0, so you cannot use the arc length formula. Whoops. So that means what we have to do is solve for x in terms of y, and we get x is equal to plus or minus y minus 1 whole to the 3/2. Now, you might say, is it plus or minus? Well, look at the picture. It's plus. Okay, so we know it's plus. So what we're going to do is we're going to be using the version of this that is the dy thing on the outside, but that means on the inside of the formula I have dx dy whole squared. So this is 1 plus dx dy whole squared. I'm integrating from the points, and these are the y values, so this is 1 to 5, which are y's. Now you have to use tradecraft, and you have to evaluate this integral, and this is a calculation of an integral. So you go through with this, and you know what I think I'm going to do, just because I'm kind of rushing talking through this. We're going to take our break now, our 10-minute break, And Claire, according to my Fitbit, it is 9:15. So it means at 9:25 we will reconvene. We're on break now, and we'll reconvene on this slide. And thank you, Claire, for your service so far.
Hey, Jim, can I ask one really quick question?
You can, but you're eating into your break, and that's okay with me. And my break will be fine. So you can ask your
It's very, very
question,
fast.
but we will return and do this. Go ahead and ask your question.
If I take the test is it timed or untimed?
It has to be timed because some students. Tell you what, I'm going to answer that after the break because some students might want to know the answer to your question too. And by the way,
Okay.
on one hand, I would say, well, yeah, it's kind of out there, but I want to answer your question. But if you'll allow me to do that, I'm going to answer that after the break, just so everybody can benefit from it. Okay?
Okay, thank you.
Okay, so we'll do that when we reconvene, still at 9:25. Claire, can you hear me?
Yeah.
Thank you, Claire. Okay, during the break, in fact, I was interacting with some colleagues here. During the break, there was a student asked a question, and I told the student, well, yes, I will answer your question, but I think this question is best answered in the for the entire class. So anyway, and I'm paraphrasing the student's question, but he was, and I am going to answer the question, but he said, well, okay, so if we come to one of these testing centers, physical testing centers, and take our tests there, are the tests going to be timed? So I am going to answer this question, but I'm sorry, because I need to unfold and give a little bit of context for my answer to the question. Once upon a time, when there wasn't COVID and there wasn't VCMs and we were just doing classes, I was putting my test in the testing center, and all students were required to go to the testing center and take their test. And they could have unlimited time. All students could have unlimited time. So that was a level playing field that was fair. And for lots of reasons, I really like that idea, and I won't go into that discussion about why I love that idea. And I hope someday we return to such an era. But so that's kind of where my head was, and that's really still where my head is. But that was then, and this is now. So we have this VCM thing. And we have some students who cannot go to the testing center, and there's the testing centers. There's all kinds of reasons for that, and so. But I also am encouraging all students who can to go to one of those testing centers. It is a safe environment. They are masked. They do social distancing. It's as safe as it can be. And I'm going to say, if you're going off to, and again, this is not a roundtable discussion, but if you're like going to restaurants or you're going to Menards or, things like that in your private life, then I'm saying, well, you will be equally safe going to one of those COD testing centers. And so I really am encouraging students to do that. But I cannot give you a carrot of saying, oh, and you get extra time on your test, because there are some students out there, and I mean, I just in my head, I know this, who maybe they're having all their food delivered, they're not going anywhere, but they'll assert, and I'm not arguing with them, but they'll say, I cannot go to a testing center to do this. So that's why that virtual testing center is there to do that. But you see, the virtual testing center, there are human beings who are hired and paid money to come in and do the virtual testing. So that has to be scheduled, and that is a huge thing and everything else. So I talked about the hours. So you see, now in this environment where there are some students who are probably going to be doing it virtual, I mean, I'm just speculating there's going to be some, no matter how much I encourage you to do the other, who, and maybe who have to, I mean, they have good reasons for doing the virtual testing center. And I talked with the head of the virtual testing thing, and I said, well, gee, I really, would like to have unlimited time. She said, no, you can't have unlimited time if you're doing it at the virtual testing center. We're hiring people, we're scheduling people to be there during those times, and so it cannot be an unlimited time. So now I'm finally getting around to answering the question. But it's not because I want it to be this way, it's because it has to be this way. To be fair, the tests have to be timed, because the virtual testing centers, anybody who uses those has to have a time test. So to be fair to everybody, it's a time test. And so it's not that I want it that way. It's not that I'm causing it to be that way. That's the way it has to be. So if you go to the testing center, which by the way, I'm encouraging folks to do that, you will have the same time limits that the virtual testing people have. But I will tell you the advantage of going to the virtual testing center is, or no, the advantage to going to the physical testing center is you don't have to go through the scheduling thing that I'm putting on the backs of the students to schedule that. So you don't have to schedule anything. You just can plan your life and say, oh yeah, I know when the testing center is open, I'll stop in there. And if something changes, you say, whoops, something changed, so I have to go a different time. You can do that. So that's the advantage, but unfortunately, that's the only carrot I've got. Now, there was a student who was asking that question, and I'm assuming you're out there, and I'm hoping that answers your question. But yes, it will be timed if you go there because it has to be fair for all students. And so that's what we've got. Okay. So that answers that question, and now we're reconvening, and we're talking about arc length. And let's see. Okay, so let's see. So I put this in front of you, and we'll just kind of, we're not beginning again, but this is what we're doing. But we had technical reasons that we could not do dy dx. So that means we're going to do dx dy. And everybody, please note, and some students don't, I don't want to say don't understand this, but don't appreciate this. Maybe this is a little bit more a trade craft. But you see, we're integrating dy out here. So that means this is dx over dy squared. So if you're integrating dy, it is dx over dy. So you want to think about that a little bit. Now we did take the derivative. Oh, okay. We decided that x was equal to positive y minus 1 to the 3 halves. So when we take the derivative, it is going to be 3 halves times y minus 1, and we subtract 1 from the 3 halves, getting a half. So this is dy dx. Now you might notice that this is a little bit of a cooked up problem because at least when you square this, this is easy to square the 1/2. So we square it, and so, but this is the formula that we have for the arc length. Okay, so then this is what dx dy is. So we get this, and we're just plugging dx dy in there, but then we're squaring this. Now, when you square 3 over 2, you get 9 over 4. And whenever you square y minus 1 to the 1/2, you get y minus 1. And by the way, you see there's arithmetic that happens here because when you square this, you're going to get y minus 1, but this is plus 1, so there's going to be some cancellation that happens. And in fact, when you do the calculation with the 1 minus 3 halves, but then you're scoring 9 over 4, you will get this thing. So this is 9 over 4 times y. You see this number cancels with this number over here. 9 over 4y minus 5 over 4 dy. Now, I will assert that what you will want to do is you will want to factor the 1/4 out under the square root, but the square root of 1/4 is 1/2, and I would jerk the 1/2 out here. And after I do that, I have the square root of 9y minus 5 dy. Well, so you have to do a u substitution. And so, you know, there's some constants that have, you're going to let u equal 9y minus 5. But when you do the change of variable, you're going to get, this is this u to the 1/2. So you add 1 to the exponent, that is u to the 3 halves divided by the new exponent, which is 3 halves, that's 2/3. And this number out here changed because of the change of variable. And so, you know, we've integrated that now, and we plug in numbers. So this is 1 over 27. And when I put 5 in there, I get 40 to the 3 halves minus 4 to the 3 halves. Now, this is the final answer that I would expect you to have, but I'm also going to tell you that, yeah, this is a calculation that you should do. And you see, I don't expect you to tell me what 40 to the 3 halves is, or 4 to the 3 halves. This is the exact answer. So I'm going to pause for a count of 10, Mississippi, in case students have questions on this example. Okay, I hit 10 Mississippi, so that's good. Okay, now we'll go to this one. It is another one. And so what we want to do is find the arc length of the graph of y equal the natural logarithm of cosine of x from x equals 0 to x equal pi over 4, and you can see a graph. So what we're doing here is we're calculating the length from here, and that's pi over 4 of this function. So that's y equal the natural logarithm of cosine of x. Okay, here we go. Now, if you do dy dx, what happens is you're using the chain rule. Now remember that that was the natural logarithm of cosine of x, so it's going to be 1 over cosine times the derivative of cosine with respect to x, which is minus sine. So you see it's 1 over cosine, that's the derivative of the natural logarithm. So whenever you do all of this calculation, you end up with this expression, which is best treated as the negative of tangent of x. Now, the reason we were taking this derivative here is because we knew that, oh, we need that derivative in the formula, so we do that, so that is minus tangent of x. But when you square minus tangent of x, you get tangent squared of x, and we know we're going from 0 to pi over 4, so this is the square root of 1 plus tangent squared of x dx. Now, often, and this is true in Calc 2, and this is true well, this is just true, trig identities are important, and sometimes there are problems that you don't know how to do unless you use a trig identity. So here we want to say, oh, 1 plus the tangent squared of x is the secant squared of x. Now, the square root of the secant squared of x is the absolute value of the secant of x. But in the first quadrant, from 0 to pi over 4, all trig functions are positive. So the square root, the absolute value of secant x, but in this interval really is just secant x dx. Now, one of the things that you learned in Calc 1 at the College of DuPage was, oh, what's the antiderivative of the secant of x? And we learned, and this was, I mean, I've taught this many times, and that's, I mean, in Calc 2, I just say, yeah, you're supposed to know this one. But that's a long lecture in Calc 1, because actually this is a thing where you kind of cleverly multiply top and bottom by 1 to get this. But anyway, the antiderivative of the secant is the natural logarithm of the absolute value of secant x plus tangent x. So you see, this is the natural logarithm, and this, all of this is the argument of the natural logarithm. So you learned this in your Calc 1 thing. In Calc 2, we just say, oh yeah, we know this. And by the way, I am going to tell you that this thing will come up again in the course many times. So, you know, sort of commit this to memory. So it is the natural logarithm of the absolute value of this. Now, it is true that the absolute values are there, but when we're from 0 to pi over 4, all trig functions are positive, so the sum of these things are positive, and so the absolute value isn't important here. It is important sometimes. And so we get that, and so we're plugging in these numbers. So we're plugging in pi over 4, and we're plugging in this. Now, it turns out that pi over 4 is a 45, 45, 90 right triangle, so you can do this without a calculator. So you just plug in pi over 4. So the tangent of pi over 4 is 1, and the secant is the reciprocal of the cosine of pi over 4, and the cosine of pi over 4 is square root 2 over 2. And so you can plug those numbers in, and then you look at 0. Well, the tangent of 0 is 0, and the secant of 0 is 1. So if you do all of that arithmetic and plug it in, you would get the natural logarithm of the square root of 2 plus 1 minus the natural logarithm of 1. Now, I will tell you, this is 0 because the natural logarithm, the logarithm of 1 is always 0. I don't care what the base is. And so this is 0. So the real answer, I mean, I would, oh, I probably wouldn't deduct points, but if I were grading someone's paper, I would expect them not even to have this here. In fact, I'm tempted to even erase that, but that's 0. So the answer is the natural logarithm. The answer you would have to give me on a test for this is the natural logarithm of the square root of 2 plus. Okay, so I'm going to pause for a count of 10 Mississippi in case there are questions on this problem. Claire, you're still there, right?
Yeah.
Good. Thank you, Claire. You see, I never know. I'm saying maybe these students are really, really good students, or maybe I'm doing a good job explaining it, or who knows what. But anyway, okay, so we'll move on. That is good. And now we're talking about a length of cable. Now, actually, this is a very important kind of a problem, and it is an applied problem. And one of the things, and this is looking ahead a little bit later in the course, because we're actually going to talk about this in. We've messed around with the Calc 1 and Calc 2 curriculums at the College of DuPage, and I don't know where you guys studied and what you did, but it turns out that there is a famous curve. Okay, let me just talk about it and I'll get there. An electric cable is hung between two towers. So there's a tower there, and here's a tower here, and the towers are 200 feet apart. By the way, I don't have to draw you a picture, but there's a picture anyway. Now it says that, and it's just telling you this, the cable takes the shape of a catenary. If you study differential equations with me, we will actually prove that that a hanging cable takes this shape. And back in the day, before everything was wireless, and back when I worked at Bell Labs, this was actually an important issue whenever we were planning facilities, because there were a lot of cables. They were in facilities and they had uniform cross sections. But anyway, the shape that the cable takes looks like that. Now, you might say, well, boy, that kind of looks like a parabola to me. It's not a parabola, but you're in pretty good company, because the great Galileo thought that was a parabola, at least for a while. But it's not a parabola, and just it takes take that as a given in this problem until you take differential equations with me or maybe someone else. The cable takes the shape of a curve called a catenary. And Thomas Jefferson, who was the third president of the United States and who wrote the Declaration of Independence, actually named this curve the catenary. But anyway, this is the equation of it. So it is y equal 75. This is e to the x over 150 plus e to the minus x over 150. Now, it turns out in applied math, this function comes up a lot. And later on in this term, because we moved it from Calculus 1 to Calculus 2, I actually had time in Calc 1, so I talked about this. But we have a name for this curve, at least if we divide by 2. And if we divide this, let's see, there's a name for this, and the name for this term, this curve that happens a lot, is the hyperbolic cosine of x. And the way this is pronounced, when we get to it, we'll talk about it a little bit, I guess, or I'm sure we will. And so this is called the cosh. That's how people read this. And that's cosh like kosher, kind of kosh. So this is the kosh of x over 150. Now, you don't have to know any of that. They're just giving you this, and they tell you, okay, an electric cable is hung between two towers. They're 200 feet apart, and the equation of the curve is this. Now, you do have to invent your own coordinate system, though, because this is an applied problem, and this is tradecraft. You have to think about this, but this is a good coordinate system to have. So you have a 0, 0 here. You got one tower that's at minus 100, another that is here, and the intercept is 150. And if you graph this, you'd figure out that the graph of this looks like this on this curve, and the intercept would be 150. But really, the thing we want to do is just find the arc length of this. So what we're really going to do is this is y equal this business, and we're going to find the arc length between the cables. Now, it really is important, and these things actually do drop down like that. I mean, there's some good physics involved there. Okay, so let's do the problem. It is an applied problem. Okay, so first thing we have to do is we have to take the derivative of this guy. Okay, so when you take the derivative of this guy, the 75 just sits there. You ought to use a chain rule. So the derivative of e to the x over 150 is e to the x over 150 times 1 over 150. That's the chain rule. And then when we take the derivative of this guy, it's going to be e to the minus x over 150. But the chain rule tells you that you have to multiply by minus 1 over 150. So you see there's an SIGN, a sign change here. Okay, so I just tried to convince you that y prime was equal to 1 over 2 e to the x over 150 minus, that's the minus sign I was talking about, e to the minus x over 150. And so we know we need y prime in our formula. So y prime, if I square it, I'm squaring this. Now, the tradecraft that I talked about earlier happens again, because you see, when I take this thing times this thing, that becomes 1. So you have to go through, so this is tradecraft again, because when you square that, this is what you get. That's why you get this constant, is because those exponents are the same. So now we're going to say 1 plus y prime whole squared. We're adding 1. Now notice what happens when you add 1. This was 1/2, but we're adding 1, so that changes the minus 1/2 to a plus 1/2 when you add 1. So this is 1 plus y prime whole squared. So it's this thing, but then think about the tradecraft again. This thing is the square of this with a plus on it. So you see, in fact, we'll see it down here. Okay, well, no, I guess it says it right here. So you see, this is the same thing as the plus with the square on the outside. That's the tradecraft again that I was talking about. Okay, so therefore the length of the cable, now we're back to formulas and stuff. So we're integrating this as 1 plus y prime whole squared. Now up here I just tried to convince you that if you square 1 plus y prime squared, you get this business. Now you're squaring a half, but you're taking the square root of it, so you get a 1/2 out in front. But this thing, you got a square on it, so the square root of this thing squared is just this business. So now you just have to integrate this. And so the integral of e to the u is e to the u. Now there you have to change variable a little bit there. Plus an integral of e to the minus u, that you change variable there again, and you get this. And then you plug in 100 and minus 100 and do the calculation. And so you get the exact answer here is 150 e to the 2/3 minus e to the minus 2/3. Now, since the guy that wrote this book is an engineer, and an engineer probably would plug that into a calculator and say, well, it's about 215 feet. But that's not what I'm asking you to do. This would be the answer that you would end up with. But this is actually an applied problem. And this is something in the telecom business we actually had to deal with. Counting to 10, Mississippi.
You said something about changing variables, and I didn't follow.
Okay, I will try to address that question. Now, I'm going to I'm going to say some things. I'm going to try not to go to the blackboard just because the blackboard is kind of clumsy. So I'm going to try to answer that right here. Okay, so in the course of doing this, you want to integrate e to the x over 150. But to integrate e to the x over 150 in Calc 1, what a student would do is they say, oh, I'm going to let u equal x over 150. And then du would be 1 over 150 dx. And so they would have to do a change of variable here somehow. And so some students would say, well, how did the 1/2 become a 75? That was associated with the change of variable here. Similarly, when you come to this one, you've got e to the minus x over 150. Well, in Calc 1 anyway, you'd let u equal either x over 150 or minus x over 150, and then du would be, a constant times dx. So there's a constant flying about there, and that constant is the 150. And that 150, though, since you need it inside the integral, you multiply and divide by it, that's going to end up giving you a 75. Now, I can talk more about that, but I'm going to pause and hope that maybe that answered your question. In fact, I'm asking you directly, the student who asked the question. Are you good with this?
I know what I need to review, so yeah, thank you.
Okay, so anyway, okay. I start my count again whenever somebody asks a question.
Yeah, I have a quick question.
Go ahead, please.
I'm having a difficult time understanding how we went from -2 up to +2 when we added the 1.
Okay, I'm going to look at something here. Yeah, okay. That's tradecraft again. Okay. So here's what I'm going to do is I am going to do a little bit more. Well, you know what? I'm going to try to do it waving my hands here now, or waving my cursor here. But here's what happens. And please try to follow along with me. And that's the reason I talked some about the tradecraft here, because gosh, it came up again. In fact, it comes up around quite a bit, I guess. So anyway, this is e to the x over 150 minus e to the minus x over 150. But we need to square this, don't we? Because we're talking about y prime squared. And I am going to ask you to, kind of, ping back with me. So this is the thing we have to square. This is something we have to square. So you understand that part, yes?
Yes, that's correct.
Good. So now what happens when we square this? Well, when you square a binomial, you're taking this thing times itself. So you're going to say, well, I square the first term and I square the last term, but then I have twice, it's -2, the middle term. I'm going to say that in a different way. X plus y, or excuse me, x minus y whole squared is x squared minus 2xy. Okay, so you see, this is going to be minus 2xy when I square this for my middle term. But what do I get when I multiply e to the x over 150 times e to the minus x over 150? Well, when I take this thing times that thing, I get 1. And I get 1 twice.
Okay.
So when I get 1 twice, it is -2. And again, I'm in no sense, I'm just saying this is exactly what I was talking about with the tradecraft. That's where that -1/2, where that -2 comes from. But when I square the 1/2, I get a 4th. So what I have here is a -1/2. But I'm adding a 1 to that. So if I add 1 to a -1/2, it becomes a +1/2. And you can see here, it's a +1/2. But, oh, that's a perfect square. That's the other half of the tradecraft that I did. And so that's what I get. Now I'm going to pause and see if maybe, and I really was sincerely trying to answer your question. Are you better now?
Yes, that definitely helped a bit. Thank you.
Okay, great. Okay, I start my count again. Okay, I hit 10 Mississippi, so I'm going on. Your questions, of course, are always welcome. Now we're going to talk about something else, the second topic. This is called the area of a surface of a revolution. Okay, now we'll look at definitions and things like that, but here's, I made this as just a comment, and this is what I say whenever I'm in class with people and things like that. If you are painting the outside of a solid, and you're just painting the outside, you're not painting the inside. So if you're painting the outside of a solid, you would want to know, how much paint do I have to buy? And so what you might do is you might calculate or estimate the area of the outer surface of it. So the question that's really being asked here is how, and not exactly this, but for some students, I think this is useful. I keep using it. I hope it's useful. So you want to think about, oh, I'm painting the outside of a solid. How much paint would I have to use? And that is the area of the surface of revolution. Okay, so, and here's the definition. When the graph of a continuous function is revolved around a line, the resulting surface is a surface of revolution. Okay, so here we go through and we do a derivation. Now I am doing this derivation because I don't want you to think that that anything I'm teaching you is bogus or anything like that. So what we're really doing is we are going through a derivation of this formula. But once you see the formula, you're going to say, oh, so is he going to ask us to derive this? No, I'm not. So, what's going to be a little bit surprising is that thing that I talked about earlier called ds, where that is the differential of the arc length. OMG, it pops up here. Okay, so here we go. The area of a surface of revolution is derived from the formula for the lateral surface area of a frustum of a right circular cone. When I first started teaching at the College of DuPage, I thought everybody would know what that is, and I learned that many people don't remember what that is, but we'll talk about it. So anyway, so I said, consider the line set. So that's just a statement, but that's what we're going to do. Consider the line segment in the figure shown below. I'm going to go ahead and show you the picture. So this is what happens, and this thing that it kind of looks like a cone. I mean, if you had a point up here and things like that, you say, yeah, that's a right circular cone. But if you chop off a piece and chop off a piece here, it is called a frustum. So this is what a frustum is. So you're taking the line. Here is the line that you have up here. So that is the line, and you're revolving the line. So it's this thing, but you're revolving it around an axis of revolution, which is there. Now, when you're doing that, you realize, oh my God, that's just going to be the outside of this thing. That's not going to be, there's no inside of this thing. It's just like if I cut this out of paper and put it together. So you see, this is going to give you a surface. So if we rotate this around, this is the surface area of a right circular cone. Now we do have a radius of the bottom and the radius of the top in the cone. Okay, so that's kind of the picture that we have. Okay, and I think I talked about all of that. Okay. When the line segment is revolved around its axis of revolution, it forms a frustum of a right circular cone. And this is a formula that is taught in geometry. Maybe you learned it, maybe you didn't. I'm not going to ask you to remember this formula, but that's what we're using. So this is equal to, by the way, it shouldn't surprise you that we're going to get a, actually, you could derive this by doing that rotation yourself. But anyway, this is just what it is. It is 2 pi times r times L. Now, what are these things? Well, R is the midpoint is the average radius of the frustum, and L is the length of the slant height of the frustum, like that. Okay, so we'll keep deriving this. So delta L, and in fact, I'm going to show you another picture. So if you looked at this, you'd say, well, okay, this is going around. I'm getting these little bands of things as I'm going around, and that does depend on X. But let's zoom in and look at the picture. So you see L is the distance along here. So that is delta L sub I for this little representative slice. And this was the curve that we're talking about, is y is equal to f of x, so it looks like that. And so this is what the representative thing is. But if we zoom in on that, we say, oh, gee, so I'm going along this, but this is well approximated by, this is the change in L, that's the change in x, and that's the change in y, and OMG, that is a right triangle, so Pythagorean theorem holds. And by the way, the distance from here to here is the arc length along that. Okay, so I need to think about where we are. Okay, so I said, well, okay, so the Pythagorean theorem holds. So delta Li is equal to the square root of, this is delta Xi whole squared plus delta Yi whole squared. And then by the intermediate value theorem, because that's a continuous function, a point d sub I exists in the ith interval. This is Calc 1 again, such that Ri is actually equal to f of di. Okay, so that means that, so we say that Ri is equal to f of di. So the formula then is 2 pi, this is Ri, which is f of di, and this is delta L, which looks like this. But now what I'm going to do is I'm going to multiply and divide, that's math tradecraft, by delta x sub I whole squared. These guys stay the same because they're just numbers. So this is the square root of 1 plus delta yi over delta xi whole squared times delta xi. So again, by some more Calc 1 things, we studied the mean value theorem in Calculus 1. There's a number ci in this interval such that f prime is equal to this, which is delta yi over delta ci. So we're going to replace this by f prime of ci. Now, that was just a representative slice, so we add all these things up, and it's going to become an integral. So it can be shown that the limit as n goes to infinity is this integral. Now, and we're going to look at the formula. So the surface area of revolution is equal to 2 pi, the integral from a to b. This is f of x. And this is the square root of 1 plus f prime of x whole squared dx. But I told you that this thing right here, and I'm kind of trying to draw a line there, that's ds. So you see, that's why we're studying this right now. Now, you do have to draw pictures here again because, well, in fact, let me just go up here and look at the picture. Okay, and there are two pictures that we're going to look like. So this is y equal f of x, and in this case, so y equal f of x is this boundary up here. But what we're going to do is we're going to be revolving that piece of the function around this axis of revolution. So, okay, so that is y equals f of x, but we're revolving around here. So what is the radius that you happen? How do you draw the slice if you're revolving around here? Well, if you're revolving around here and you draw the slice this way, the radius that you're getting for that is f of x because it's a point on the curve. What's the other dimension though? how far are you, well, that's actually what the other, so this is r equals f of x, and the distance that we're out is x. Similarly, what happens down here, if we're going down the other, r is equal to x, and actually up here, you could say r is, well, f of x is y. So up here it's y, and down here it's x. Let's just summarize this then. Let y equals f of x have continuous derivative on the interval ab. The surface, the area S, that's the surface area of a revolution formed by revolving the graph of f about a horizontal or vertical axis. And you might say, does it matter if it's horizontal or vertical? Well, heck yes, it does. So we're going to talk about that is this is dx, and r of x is the distance between, in fact, to tell you the truth, I think I'm going to go to a different, no, I guess I can't. I have to stay on this. Is either this one, where r of x is the distance between the graph of f and the axis of revolution. Now, sometimes that is x and sometimes that is y, but it also could be something else because we may or may not be revolving around the x or y axis. Or if x is equal to g of y. So my point is, you either can do this. So you see we had different formulas for ds. ds could be with the dx here, or it could be with the dy here. This is probably, and here they're saying exactly what I said earlier, that, oh, gee, sometimes you can talk about this as being ds, where ds is either a dx version of ds, or ds is a dy version, okay? Let's do an example which I think will help things a lot, okay? So let's find the, and I am going to pause for questions at the end of this, and I realize we're getting kind of near the period. That's kind of okay. So find the area of the surface formed by revolving the graph of y equals x cubed on the interval 0, 1 about the x-axis. Now we're doing, so, and again, I do expect you to draw the picture, so this is what you would draw. We're going around this axis, that is y equals x cubed. So that is what we get. Now notice here that we're going around the x-axis, and so the distance that we're up, that r of x that I'm talking about, is f of x, which actually is y, and y is x cubed. Okay. So the distance between the x-axis and the graph is f of x. And because f prime of x is equal to 3 x squared, you see if you take the derivative of x cubed, it's 3x squared. So we can plug in, here's the formula we get. We're using the dx here. So f prime, first of all, the distance, let's go back to the picture just for a moment. So the distance here, the radius is f of x, which is x cubed. So that is x cubed. So that's the distance, r of x is x cubed. This is the ds, but we're doing this in terms of x. We could do it the other way, but we're doing this in terms of x, and f prime was 3x squared. So that's why I get an x cubed there. That's why I get a 3x squared there. So I have to compute this. This is going to be 9x to the fourth. And let's see. So you know, that's what I get when I'm taking the square root of that. And here you are going to this is a 9, right? And so if you when you square it, so anyway, when you do this calculation, then this is 1 plus 9x to the fourth to the 1/2. Now we are going to have to deal with the 9, and so whenever we're doing this this integral, we're going to have this integral. Now it turns out though that this integral is kind of can be done by u substitution, because if we let u be 9x to the fourth, then du is 36x cubed dx. So then we can integrate this. So this is going to be add 1 to the exponent, divide by the new exponent, and substitute in the numbers, and we get pi over 27. This is going to be 10 raised to the 3/2. That's the exact answer, minus 1. This is, the kind of question that I might ask. Now, I know how much time there is and things like that, but I am going to pause and answer. And again, after we drew the picture, we were just using this formula right here. So that was the formula we're using. And you see it is intimately related to the arc length. Okay, and I am watching the time, but I'm going to count till 10 Mississippi and see if there's questions. I hit 10 Mississippi, so that is kind of it. Again, no class tomorrow. Yeah, this is a learning objective. It's one of the things that we should talk about, and but I'm pretty much thinking that we covered it. There are some other examples that I have here, and there are other examples in your book, and so forth. But I think we got to where we needed to. This is covered. And again, now this is a general call for questions. I'm only going to count to 5 Mississippi. Any general questions anybody wants to ask? I don't know if that's somebody asking a comment or leaving. That's probably people leaving. Okay, so I'm just going to, I guess, dismiss you. I am going to go back to Blackboard. I'll check to see if there is a comment there, because I need to shut down the recording. You guys be careful. Alan has his hand up, so I will call on Alan, I guess. Go ahead, Alan.
All right, yeah, it's just a quick question. Is there any way that we can access that PowerPoint that you were just going over?
I am going to, you see, I never know where I'm going to be, so things like that. But one of the things I plan to do over this 3-weekend thing, given what my schedule is today, it's probably not going to happen until later. But I'm going to post. I will post them in your syllabus tab. But now I'm posting things that we actually covered, not random notes that I put there. So yes, you will be able to do that. You can't right now, but I'm going to let you know about that. Okay.
All right, thank you very much.
Okay, I'm going to shut this out. You can access the thing I'm stopping